In this section, we're looking at definite integrals. Definite integrals are used to find the area under a graph. So far, we've done this by estimating, but integrals will be finding exact values. Now let's look at the patterns we've been using to find these. When we were looking at these, we were taking various x values, or really the y values were what we were interested in as we calculated these things. So for our heights on these, we would start with whatever our first value was here. Maybe in this one, we're using midpoints to be f of 1 if we're going from 0 to 4. And then also at f of 3. And then we would multiply that by the width of each of these. So this is going from 0 to 2, 2 to 4. So all those have a width of 2, so we can just distribute that out. So if we're, again, going from 0 to 4, and all of them also have the same width, this time the width of each of those is 1. If we want to be more accurate, we can take more rectangles. And we would use the same process. F of the first one plus f of the second one plus f of the third one. And we go across there finding each of those values until we get to our last interval here, whatever our last one is, and then we multiply that by the width of all these intervals. And this time, since we're going from 0 to 4, we have 8 rectangles, so each one of those would be 1/2. Okay, but as we get more and more rectangles, we don't want to keep doing that. We want to recognize a pattern in this. And what we're doing in each one of these is we're adding all of our f's together, and we keep adding them until we get to our last one, which we might call xn. We then multiply that by the width. Now, one way to do that, if we think about this as going, we said from 0 to 4, so we could say maybe 4 minus 0. So it has a width of 4 there, but we're dividing it by the number of integrals we wanted. So we're going to have n intervals, which also tells us how many x's we're going to use here. And this is our pattern that we're going to use. We can put this into sigma notation, which would be written like this, saying we're starting with our first x, going to our nth x. Okay, so that just tells us how many. It doesn't say we're starting at x equals when we're saying we're starting at our first x. The delta x then is telling us our change in x. And this was what we did when we found this last part here. We find out how wide each one. So like this one, we went from 0 to 4. So we had a length of 4 here divided by n rectangles. Notice also that this is really just giving us our area equals base times height. The delta x was our base, and our y values were our heights. The sigma notation tells us that we're adding them all together. So if I look at this one, I don't know exactly what f of x is, but if I want to write an expanded form, it looks like we're using right endpoints here. So we would start with f of x1 plus f of x2 plus f of x3. And then we would look at the width of our interval. Notice we're going from -4 to 3 here. So 3 minus a -4 divided by the number of rectangles we have, which we are looking at 7 rectangles. So that'd be the expanded form. If we want to put this in sigma notation then, which would be a much shorter version, we'll always start with k equals 1, and then going to n, in this case we had 7 rectangles. We'll then take f of, well, we're starting with our first x, so we'll call this xk, which will tell us we plug in x1, x2, x3, keep adding them together, and then we multiply this by our delta x. But our delta x here is this value right here. This is our delta x. This is telling us how wide each one of these, how much x changes for each rectangle, which, as we saw here, this is actually 7 over 7, which is equal to 1. So I could multiply this one by 1. It's now in sigma notation. Now remember again, the more rectangles that we have, the more accurate our area is going to have. And so with sigma notation, what we'll want to do is move into the concept of limits so that we make n infinitely large, which makes the widths of our rectangles infinitely small. Then when these widths are infinitely small, the area is going to become exact. And this leads us to the idea of the definite integral. With the definite integral, think about how with our derivatives we took infinitely small pieces to find our change, and so we're using the same concept with these. But we're going to use a different notation now. Rather than the sigma notation, we're going to use a new notation that's more helpful in calculus. We're also going to be able to use the derivative to apply to these areas. So defining the definite integral, this is the notation that we'll use here. We use this large S-shaped thing where A is the lower limit of integration. So like on this graph, this -4 would be our A. The B here would be our upper limit. So in this one we're going to 3, so that would be our B. And so on this one we're going from -4 to 3. F of x is the function we're using, so whatever function we have here. In this one we don't know what it is, we'll just call it f of x, so I'll leave it like that. It'll just be our equation in terms of x. And then dx will just be tagged on the end. Now the x is important. That's the variable of integration. That tells us what variable we're doing this with respect to. Since this is x in here, then we will also use dx here. This whole thing taken together as a piece is called the integral. When we work it out, we say we are integrating. So if we want to write this as a definite integral, we look first at where we're starting and stopping. Now that's given to us here, not in the sigma notation. We know that we're starting at -1, going to 3. Our function, rather than using m's, we're going to just change this to x. 3x squared minus 2x plus 5. And we should put parentheses here, although some books will disagree about that. And then the delta x, rather than using that, we change that to dx. Everything between the integral and the dx is sandwiched in there inside the parentheses to show that that's what we're taking the integral of. So the definition of the area under a curve. So if we're looking for the area of under a curve, and we think about this integral as being non-negative, if our function f of x is always positive, then the area under the curve is our integral. So we can think of the integral as area, but only if our function is positive. If we move down to a situation where we have negatives in here, then we can no longer think of the integral purely as area, but we need to think of the positive parts and the negative parts separately. Okay, so if we want to evaluate this integral, we can think about it as area. So first let's look at the function that we have in here. We should recognize that this is the equation of a circle, or actually a semicircle here. So if I'm looking for the area of a semicircle, well, a circle would be pi r squared, and a semicircle would divide that by 2. We have a radius here of 2, and so that's what we'll do. This integral will be equal to pi r squared, where our radius is 2, divided by 2, which gives us 2 pi. So for now we're going to be finding integrals just using area formulas. When we look at an integral and area, they are related, but they're not the same thing. So the way I have this written right now is actually wrong. These are not equal to each other, because what I have here in the first one, it says the integral going from 0 to 2 pi. If I'm going from 0 to 2 pi, notice that this area over here is going to be a positive value. This one is a negative value. There is symmetry in the sine curve, so this integral here is actually equal to 0 because they would cancel out. This part over here, though, is looking at the area. Since I'm subtracting this part down here, which is negative, it's kind of like I'm turning it into a positive value. And so I'm finding the area here, and this area here, area 2, but this is after I've taken the absolute value of whatever this is. And so this here, as I'm splitting it up from 0 to pi, so I find that intersection with the x-axis, 0 to pi, and then continue from pi to 2 pi, but I change the sign of this by subtracting it, this will find the area for that section. So if we're looking at a section of a graph that is negative and we want to find the area, we'll need to subtract those negative proportions so that really we're adding the area. We're turning those values into positive values so we have a positive area. If we're looking for the integral, though, we'll be looking at the area above the x-axis, subtracting the area below the x-axis. So we might have values above and below that are actually canceling each other out. So be careful what they're asking for. Again, integrals can be negative. We add and subtract according to the sign. Area cannot. We need to change the negative sections to a positive section before we add them together. If we have a constant value, then that's always going to give us a rectangle. So the C is a constant, the graph of a constant. And so to work out that integral, in this case here, our constant is c, so the integral would just be whatever that constant is times our length. We think about this rectangle here, the width of this would be b minus a, the height of it is c, and so that's why we're getting c times b minus a. So here's an example. To make an integral out of this, we're going from 7 to 9. Our function is a constant here. The line y equals 75. So we just write it as 75 dx. To work that out then, since it's a constant, we would take that constant times 9 minus 7, which gives us 150. We would then look at our units here, which would be in miles. In this problem, we're asked to find the integral going from -1 to 2 for the absolute value of x over x. Now notice, absolute value of x over x would be equal to either 1 if x is a positive number, but if x is a negative number, this part will say negative, and we would have a -1 for all negative values. So working this out, we are looking for the integral. There's nowhere on there that is asking for the area. We want the integral. So when I find my area, this part here has an area of 1, but these are negative values because they're below the axis. This part up here has an area of 2. Since it's the integral I'm looking for, not the area, we keep this as a negative value, -1 plus 2. And so my integral is equal to 1. The negatives and positives are canceling out.